Good morning, everyone. I'm waiting for a few more people to join up. Hey, what's up, Courtney? Thanks for stopping by. All right, cool. We've hit the critical number for me to begin. So, what have we learned about simple harmonic motion so far? We have learned that the equation of simple harmonic motion is minus omega squared times the quantity x minus c equals the acceleration. So if your equation of motion is this, then that means that your position as a function of time is going to be c plus a cosine of omega t plus phi. Okay. So what does that mean? So this is oscillation about the point C. Okay. A and phi are initial conditions. Okay, so that depends on when you start the motion and how big the motion is. And then omega is related to the period. So omega is, the period is 2 pi over omega. All right. So that's the information we're going to need for today. So let me just remind you about the mass spring system. The mass spring system is, we've got a spring. The spring has a stiffness K, and it's attached to a mass M. And we're going to assume that the mass, that this is x equals 0. Okay? We pull the mass some amount to the side. So the amount that the mass is pulled to the side, that would be the amplitude of the motion. And we release it. And it's going to go back and forth like this. Okay? So the equation of motion in this case is Newton's second law, net force equals ma. The net force in this case is the elastic force. By the way, that's defined as x equals 0. So we have minus kx equals ma. Divide both sides by m. We get k over m times x equals the acceleration. So if we compare this, to the fundamental equation of simple harmonic motion, minus omega squared x minus c equals a, we can see that this is the same form. So the mass spring system does SHM, okay, with omega squared equals k over m, so by comparison, and c equals 0, okay, because this is the same as x minus 0. All right, and I should say this is a horizontal mass spring system. So we're going to talk about the vertical mass spring system a little bit later on today. Okay, so in particular, that says that the period is 2 pi square root of m over k. So this is the period of the mass spring system. All right. So what I wanted to talk about in particular today is the is energy and the mass spring system. So if we think about the mass spring system, the energy of the mass spring system is going to be kinetic energy plus potential energy. In fact, we can think about simple harmonic motion as an exchange between kinetic energy and potential energy. So we have potential energy goes into kinetic energy, goes back into potential energy, goes back into kinetic energy. And so it's energy passed back and forth over and over between kinetic energy and potential. The kinetic energy is 1/2 mv squared. The potential energy is elastic potential energy, 1/2 kx squared. All right. So what I would like to do is go ahead and prove to you that the energy is conserved. Okay. So if we take our position as a function of time, so a cosine of omega t plus phi, all right, and we take the derivative of that, we can get the velocity as a function of time. So I've already done this derivation before for taking the derivative of this, so I'm not going to spend too much time on it, but the answer is minus a omega sine of omega t plus phi. Okay? So I'm going to take this and plug it in for x, and I'm going to take this and plug it in for velocity. Okay? So I get 1/2, all right, m times, and then I have to square this, so I get a squared. Well, first of all, minus squared is minus 1 squared is just 1. A squared is a squared. Omega squared is omega squared. And then I have sine squared of stuff. Okay, I'm not going to bother writing this stuff down because it's going to be the same no matter what. Okay. Now, for this potential energy term, we are going to get 1/2 k x squared. So squaring x gives me a squared cosine squared of stuff. All right. Now here's the thing. If we take omega squared, this definition of omega squared, and we multiply both sides by m, we're going to get m omega squared equals k. All right. So if we look at this, see how I have m omega squared right here? So this is actually going to be 1/2 k a squared sine squared plus 1/2 k a squared cosine squared. All right. And so you can see we have sine squared plus cosine squared, which is 1. So what that means is that the energy of the mass spring system is 1/2 Ka squared. Isn't that nice? So I like that. So basically what this says is that the bigger the amplitude is, the more energy the vibration has. I think that's fairly obvious. Some other things I want to talk about. So we're going to derive some additional equations. So this equation right here, if you think about sine, the sine function wiggles between +1 and -1. Okay. The sine function wiggles between +1 and -1. So if we think about a omega times sine, that means that a omega times sine is going to wiggle between plus a omega and minus a omega. So what that means is that the maximum speed is going to be omega times a. All right? The maximum speed in the simple harmonic motion is omega times a. All right? And so we can use this relationship we can show that Vmax squared is going to be omega squared a squared, which is going to be, because omega squared is k over m, it's going to be k a squared over m. Okay? So I can take this, I can use this relationship and plug it in here, and I can write that the energy can also be written as 1/2 m Vmax squared. Okay? So we have 3 different formulas for the energy in the mass spring system. We can think about it as all potential energy, all kinetic energy, or some combination of kinetic and potential energy. All right. And then there's this formula for the maximum velocity. If we take the derivative again, it's going to bring out another factor of omega, and we'll be able to see that the maximum acceleration is omega squared times a. All right. So let me do a drawing here, and then we'll do an example. So if we think about a mass spring system undergoing some motion, okay, the mass, let's suppose that the mass starts out here. Here's x equals 0. All right. Here is x equals a. And here is x equals minus a. So if we think about it, what's going to happen is the mass is going to start to move this way. All right? So when the mass is at its extreme point, its velocity is equal to 0, and the energy is 1/2 Ka squared. So it's all potential when it's at its extreme point. Okay? Then what's going to happen is the spring is going to pull the mass to the right, and so the mass is going to, pull it to the left. The mass is going to start going to the left. Okay? Notice how it has potential energy because the spring is still stretched, it also has velocity. So at this point, we have both kinetic and potential. All right. And then the mass is going to swing through equilibrium. And when it swings through equilibrium, it actually has its maximum speed, because here at x equals 0, it has no potential energy. Okay, so therefore it has all kinetic energy. And so here we can think about the energy as 1/2 m v max squared. Now, once it passes through equilibrium, now the spring is starting to be compressed, so it's going to start to slow down. Okay, so here the energy is comprised of both potential energy and kinetic energy. All right, and then it's going to reach x equals -a, so the extreme point on the other side. And once it reaches that extreme point, it has no velocity. And so therefore the energy is all elastic potential. All right, and so it just does this and it goes back and forth. So we have this exchange between elastic potential energy to kinetic energy. We have all kinetic energy when we are in the center of the oscillation, and we have all potential energy when we're at the extreme sides of the oscillation. And when we're not at the center or at the extreme, we have both. Okay? The energy is the same no matter what, but what I'm doing in writing this out is I'm showing you what form the energy is taking at each moment. All right? So let's do an example. All right. Let's say that all right. So let's say that a 3 kilogram mass is attached to a spring of stiffness let's say 100 newtons per meter. Mass is pulled back let's say 0.4 meters and released from rest. Okay. At x equals 0, the mass has a completely inelastic collision with a 2 kilogram mass. And we're gonna say at position 0 and also at time 0. Okay. Write the position as a function of time. Okay, so let me break this down. So we got this mass, okay, and it's stretched, connected to a spring and stretched. Once the mass, and we'll say that here is x equals 0, there's this other mass that's right here. Okay, the mass, so this is the 3 kilogram mass. This is the 2 kilogram mass. So the mass is released from rest, and it starts heading this way. Now, once it gets to the center, okay, this 2 kilogram mass gets dropped onto the top. Okay, like that. And then it's the pair that is going to oscillate. See what I'm saying? So, so if we write x of t is going to be of the form a cosine of omega t plus phi. All right? So first of all, what we want to do is we want to figure out what is the amplitude. Okay, and the amplitude is not 0.4 meters. It's going to be less than 0.4 meters because when we drop this 2 kilogram mass on top of it, some energy is going to be lost in that completely inelastic collision, which is going to make the final amplitude less. All right. So what we're going to do is we're going to say that the energy at release is going to be equal to the energy just before collision. All right? Because during the collision is a completely inelastic collision, so energy is going to be dissipated as heat. But the energy at release is going to be equal to the energy. So energy is conserved up until the moment of collision. Okay? The energy at release is all elastic potential. Okay? Just before collision, the energy is all kinetic because the collision happens at x equals 0, where there's no elastic potential energy. All right. So we can use this. So let me plug in numbers here. I have 100 times 0.4 squared. So the amplitude before the 2 kilogram mass is dropped on is going to be 0.4. Equals 3 times V max squared. So I can take this and I can solve for the maximum speed that it has just before the collision. And we get that the maximum speed is 2.3 meters per second. Okay, so that's going to be the first part of our problem. But now we have a collision, and in a collision, conservation of momentum is king. Okay, so the momentum before the collision is going to be equal to the momentum after the collision. Now, after the collision, okay, we have both masses moving together. So the final momentum is going to be 5 V final. The initial momentum is the momentum of the 3 kilogram block, which is going to be 3 times 2.3. So we can take this and we can find the speed after the collision. And so that gives the speed after the collision is 1.38 meters per second. All right? So you can see that it slowed down a little bit. It went from 2.3 to 1.38. All right? So now what's going to happen is the pair is now going to compress the spring Okay. And so we want to know how much does it compress it? What is this distance right here? Because that's going to be the amplitude after the collision. So once again, after the collision, energy is conserved. So what we're going to do, okay, is we're going to say the energy just after the collision is going to be equal to the energy at full compression. Okay, so just after the collision, we have 5 kilograms moving to the left at 1.38 meters per second. Okay, so we have 1/2 times 5 times 1.38 squared. At full compression, we have elastic potential energy. All right. So that is going to be 1/2 K, which is 100, times A squared. So remember, the collision is going to reduce the amplitude because during the collision it slows down. So I'm going to work that out and I'm going to solve for the amplitude. Let me see. So we got 5 times squared divided by 100. So the amplitude is now 0.31 meters. Okay, so that tells me that this number right here is 0.31. All right, so now I have to figure out what is omega. All right, omega from the previous page here, omega squared is k over m. So omega is root k over m. All right, which is going to be square root of 100 over 5 because so why is it 5 and not 3? Because we're trying to get the position as a function of time after the collision, and after the collision there's 5 kilograms going back and forth. Okay, so we get square root of 20, that's 4.5 radians per second. All right, so we're going to get cosine of 4.5 t plus phi. So now the question is, well, what is the phi value? And that's pretty easy, okay? We can see that the collision happens at time equals 0 and at x equals 0. Okay, at time equals 0 and at x equals 0. So we know it has to be a sine function. Okay, it has to be a sine function because the sine function has it equals 0 at time 0, right? Sine function starts at the origin, not cosine. And furthermore, it's going to the left. Okay, so negative sign goes to the left because it drops down to negative values of x. So this is going to be x of t equals negative 0.31 sine of 4.5 t. That will be the position as a function of time after the collision has occurred. All right. So just a quick last thing that I wanted to talk about is what if we have a vertical mass spring system? Okay, so instead of the mass is going side to side, it's going up and down. So now gravity is impacting the motion. So here's our, so we have a mass that's attached to a spring of stiffness K. All right. So our Newton's second law in that case is going to be net force equals ma. The net force is elastic force minus kx, or you could say minus ky if you wanted to, and gravity. Okay. So I'm actually going to factor out a k from this side. So I have minus k times, actually I'm going to factor out minus k. All right. And then I'm going to divide both sides by m. All right. So let's compare that with the fundamental equation of simple harmonic motion. Who could tell me what is the c value? What is c equal to if you have a vertical mass spring system? If you have a horizontal mass spring system, the c value is 0 because it's oscillating about x equals 0. But what about if you have a vertical mass spring system? Type it in the chat if you know. Excellent. Yeah, it's minus mg over k because we have, see how this is minus c and that's plus, yeah. So it's got to be minus mg over k. And what we can see is that omega squared is still k over m. So the lesson here is that if you have a vertical mass spring system, the period is unchanged because omega is unchanged. So the period is unchanged. That's really important. So you could have a mass spring system that's on a planet that has extreme gravity. As long as the gravity isn't so strong to break the spring, the period is going to be the same whether it's bouncing up and down. You take it to another planet, it's going to bounce up and down with the same period, no matter where you take it. But what does change is that if you have a vertical mass spring system, it's no longer oscillating about x equals 0. The spring is going to sag below its equilibrium point, and it's going to oscillate about a lower position. Okay? And the bigger the gravity is, the more it's going to sag. All right? So if you have a vertical mass spring system, I'm going to say this one more time. If you have a vertical mass spring system, the period is unchanged. Gravity does not change the period, but it does cause the spring to oscillate about a sagging position.